So yesterday you did the polar bear penguin article, and what was that about? What? Electronegativity and the polarity, right? So if I'm looking at the periodic table and they are two atoms in the same period sitting right next to each other, what can you say about their bond? Is it polar or nonpolar? Nonpolar. If they're far apart from each other, then we could say that they are polar. Okay? And then you have to sometimes look at numbers to determine whether it is going to be polar or nonpolar. So, and those are the bonds. Today we're going to talk about polar and nonpolar molecules, but that is for the bonds. So let's watch this video. This is going to be over the VSEPR theory, and then we're going to get into the notes. So if you have your phone out or whatever, have earbuds in, you need to take those out and pay attention. Okay.
To write electron dot formulas on a piece of paper, which is a flat sheet, and we're kind of limited to the two-dimensional world, you have to really start thinking about how molecules really look in a three-dimensional world, because that's the world that molecules actually live in. The simplest model for modeling this type of behavior, and it actually works rather well, is called the valence shell electron pair repulsion theory. And the name's probably scarier than it actually is as far as it works. We often just call it the VSEPR theory, and then we kind of just say it all together, VSEPR theory. So you'll hear me say VSEPR theory from now on when I mean the previous. So the way it works, and the name kind of gives it away, is you take your electron dot formula and you simply count electron regions around the central atom, and you realize that each of those regions is a negatively charged region. And so it's going to repulse all the other negatively charged regions, and they're going to try to get away from each other. They can't completely get away, though, because the nucleus of the central atom is holding them in. So what they do is they try to get away from each other, but they're still held by the central atom. This leads to distinct molecular shapes. And the easiest one is two regions. If you only have one atom on one side and one on the other, and they try to get away from each other, you get a fairly linear type molecule. And so that's the first one. Two regions gives you linear shape. The bond angle is 180. Stepping up to the next one, three regions. You count the regions around the central, there's three. If three regions try to get away from each other, you basically get a nice kind of pie shape. It's like taking a pie and cutting it into perfect thirds. So you get a 120-degree angle all the way around for those three regions. Both of those regions are still planar. They still look just fine on a sheet of paper. It's when you get to four regions that you have to go to the third dimension. You have to go three-dimensional. And what this gets you is a shape that we call a tetrahedron or tetrahedral geometry. It's four regions around a central, all perfectly symmetric. And if you take a look and spin the molecule around and look at it, every region is equivalent. And the bond angles are now down to 109.5 degrees. That's a tetrahedral geometry. So as you can see, the bond angles are getting smaller because we're bringing in more regions. We started at 180 for linear, 120 for trigonal planar. Now we're down to 109.5 for tetrahedral. So that really sums up most of what we will use, especially in organic chemistry. Now, in addition to those, you can have expanded octets, which gets you 5 and 6 regions. So to handle those, you got to go one step further. The 5 regions is a little bit complicated, but it's really just a combination of 2 and 3. You're going to have 2 atoms linear, and then the other 3 are going to be trigonal planar perpendicular to that. When you look at the shape, you see what we call a trigonal bipyramid. We call it a bipyramid because you can look at the pyramid going up to the top atom and down to the bottom atom. Those are 2 little pyramids pointing in opposite directions. That's trigonal bipyramid. The last one is 6 regions, and when you get up to 6 regions, you get something that should look somewhat familiar if you've ever studied XYZ coordinate planes and coordinate points. everything's 90 degrees apart or 180. It's like the x, y, and the z axis of three-dimensional space. You put one atom in each space, you get 6 total. Bond angles are either 90 or they're 180. You might go, why is it octahedral when there's 6? Well, if you close up, if you take every point and make a line, you get a closed three-dimensional object with a total of 8 sides. 8-sided enclosed figure is an octahedron, and so we call it an octahedral geometry. So those are the other two that are part of VSEPR theory. When you put all 5 of those together, you've got all 5 of what we call our electronic geometries around a central atom. And that is at the heart of VSEPR theory.
Okay, so let's talk about VSEPR theory. So VSEPR stands for valence, spelling valence wrong, spelled it all day today, oops. Where am I at? Okay. So, valence, shell, electron pair, so these are the electrons which are in our valence shell, our outer shell. And they repulse each other. So what does repulse mean? If something repulses you, to push us away. Okay? So what the VSEPR does is that put repulsion in that outer area. So here is my atom, and on either side I have another atom. So what I'm looking at is the valence electrons, these electrons right in here that are being shared, all right, those electrons, they're going to repulse each other, and when they repulse each other, they're going to be set apart as far apart as possible. So for this set of electrons to get far apart from this one, it has to be 180 degrees angle. All right, if these sets of electrons right here start to move closer this way, then these electrons are going to move the opposite way so that we can keep that 180 degree angle. For this example. Okay? So this would determine the shape or the molecular geometry of the atom. By the end of today, you should be able to draw the Lewis structures. You should be able to, once you've drawn the Lewis structure, tell me its shape. Once you know its shape, you should be able to tell me if it's a polar molecule or a non-polar molecule. And I would guarantee you that that will probably be a free response question, having to do all that. Okay? All right, so in your notes, we have this thing here. What I would write down if you're writing, I would make sure that you know the molecular structure. So we have 5 molecular structures that we're going to talk about. We have linear, trigonal planar, tetrahedral, trigonal, pyramid, and bent.
Don't need a V-shape.
Or if you want to call it V-shaped, you can, but I don't call it V-shaped. I would know those 5, and we're going to add all this information into it. In a linear structure, the angle from here to there is 180. You need to know the angle is 180 degrees. You need to know that there are, so this is bonds. I'm going to put areas of bonds. So you have 2 areas of bonds. Two areas of bonds. And you see what the Lewis structure would look like if you were to draw it, like this. If I add another bond, all right, now I have 3 bonds. Now when I add that other bond, my angles get a little bit closer, and now between each angle, it is 120 degrees. If I look at this on the outside of this, this makes a triangle. So, and it's flat. So it's trigonal planar. Trigonal planar. Three areas of bonds. Again, this, you could have a double bond right here. So you could have 4 bonds, but there's 3 areas of bonds. Let's stick another atom on there. Now we have 4. In here we use Greek prefixes. So the Greek prefix is tetrahedral, tetra for 4, tetrahedral. The bond angle between any of these bonds is 109.5. No matter which way you look at it, it's 109.5. And 4 areas of bonds. Okay. What if I have 4 areas of bonds, but I don't have 4 atoms to put in all 4 of those areas? So what happens is this time I only have 3 atoms. So I have 3 atoms bonded. But what do I have now? I have an area for 4, but this time I don't have 4 atoms. I have 3, and I have what on the central atom? Electrons, and we call those lone pair. And plus we have 1 set of lone pair electrons. We have 1 set. So right here we can have another bond, but we don't have one. So we have these lone pair electrons. So we have 3 atoms and 1 set of lone pair electrons. 3 atoms, 1 lone pair set of electrons. I guess set and pair is kind of the same word. I don't know. The angle still stays the same, okay? Because we still have an area of electron of negativity here. So now what if I pull another atom off? Now I have, this time, 2 atoms are bonded. But now I have 2 sets of lone pair electrons. And we call this bent. Okay? So if you look at this, how they draw the Lewis structure, it looks linear, right? But it's not linear because of these extra electrons on the central atom. This extra area of electrons. It is bent. That's the number 1 mistake students will do. They'll draw it correctly, and they'll call it linear because it looks linear. But it's not because of these lone pair. So no matter what, I could pull these atoms off here, and any time, it doesn't matter which atoms I pull off, there are still electrons there, and it's always going to be 109.5 degrees.
So we're going to have to know that.
Huh?
Is there any way to know that just by looking at the picture? No?
looking at the picture and saying if it's the shape?
Linear or bent? Is there like there's a way to?
Yeah, because if it's linear, if it looks like that and there's no lone pairs,
Okay, but there's only lone pairs on it. It's not
bent
like-
always has lone pairs. Bent will always have lone pairs. And yes, you've got to memorize linear, trigonal, planar, tetrahedral, all those. Any questions? Everybody good, or you need a second? Good? Okay. So, before we move on, some words you need to know is dipole. So, di is 2. Pole is our areas of positivity or negativity, like a pole, the pole, positive pole and negative pole of a magnet. So, a dipole means that they are 2 areas with opposite charges. And you'll see, we will call those, that's a delta, lowercase delta. So if you have a dipole, you have a partial positive and a partial negative. So that delta, that half an 8 or S or whatever you want to call it, means partial positive. And then what we have is, we've talked,
2 areas of opposite charges.
opposite charges.
One area is positive.
Because all the electrons are being pulled toward the other side. Yes. So now what you need to know is polar molecule versus nonpolar molecule. So a polar molecule. To look at a molecule and say it's polar or nonpolar. A polar molecule is asymmetrical. So I can draw a line of symmetry, and it may look symmetrical, but if I draw a line of symmetry somewhere else, and it turns asymmetrical, then it's polar. Okay? You have to be able to draw that line of symmetry everywhere and see that it is symmetrical every time. If it's not symmetrical every time, then it is a polar molecule. Any molecule with lone pairs. Lone pair electrons on your central atom. Those are polar. So we had 2 examples a while ago. We had bent that had lone pair electrons, and we had trigonal pyramidal, which had lone pair electrons. Those will always be polar molecules. Because they have lone pair electrons, they will always be polar molecules. A nonpolar molecule is symmetrical. So any way I slice it, it looks the same on either side. So that means all the atoms are going to be the same, bonded to that central atom. And there are no lone pairs. No lone pairs.
Is that up there? So it's saying 1 and not 1.
It's asymmetrical and lone pair of electrons on central atom. Lone pair electrons on the central atom. Okay? You ready to start drawing these?
Nope.
We're going to be experts by the time the test comes. Yes. Test is on Friday. All right.
Wait, the next week? When is your test next week?
I don't know when your test next week is.
Wait, so we're going to have a test this week and then our finals.
Okay, and then this is just showing polarity. You can see that this is symmetrical, so this is a nonpolar. This is symmetrical, so this is nonpolar. And those up there are asymmetrical, and we have those lone pair electrons. Okay, so some things you need to know is that an atom, you can have a polar bond, but the molecule can be nonpolar. So if I were to draw this, the bond between the C and the H is polar, right? But the molecule as a whole is nonpolar, because the electrons are all spending its time over there by the C. So that, and it's cut it any way you want to, and it is symmetrical. A linear molecule can be polar or nonpolar. And then two identical atoms, because they have the same electronegativity value, they will always be a nonpolar molecule. It can never form a polar molecule. So let's draw. I'm going to go to NH3. NH3. First thing we need to know is needed, available, shared. So how many are needed? How many are needed? 14? 14. How many are available? 8? How many? 8 are available. So that difference is divided by 2 means we have 3 bonds. Who goes in the middle? N. We have H, H, and H. Draw in your bonds, which each bond is 2 electrons. So 2, 4, 6. We've used 6 electrons. All of my H's are happy. I have 2 electrons left over. Where do they go? On the nitrogen. What is the shape? What is tetra? Are there 4 bonds? Or 4 areas of bonds? No. So trigonal pyramid. Trigonal pyramid. Nope. Polar, nonpolar? Polar. Let's do BF3. BF3. Needed, available, shared. How many are needed? Eight times 4 is, or 8 times 3 is 24, plus my 6 from boron, 30. Boron special. How many are available? 21, 22, 23, 24? So we are sharing 6 divided by 2 means how many bonds do we have? 3. Boron in the middle. Fluorine, fluorine, fluorine. Put in your 3 bonds. 1, 2, 3. Now we finish out the octets on fluorine. So boron, so we've used 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. I have no electrons left over. I've used all 24. Boron has its 6. Each fluorine has its 8. So what is the shape? So it's trigonal planar. And what is its polarity? I would say it's nonpolar. It is nonpolar. I mean, you have the three, you have this triangle like this. So anyway, if I were to slice it like that, you have that symmetry right there.
How do you know if it's nonpolar or polar without the subtraction?
Without the what? Without the, oh, my NAS?
No. Like the electron.
You don't need it. You look at we're looking at the molecule overall. So molecule overall, where are the electrons going to spend? Are they going to spend at equal time everywhere here, equal time here, equal time here, and equal time here? Probably not. They're going to spend most of their time around the nitrogen. So that means it's polar. So if they have the same atom all the way around them, it is going to be a non-polar bond, or molecule, non-polar molecule. The difference between that one and that one, lone pairs.
Okay, you can always determine it.
Anytime there's lone pair, polar.
Oh, okay.
Lone pair, make it polar. Yes.
How come on that one you start on the actual, on the other one you start on the, like, you say you start like drawing the dots on the F?
Because H's are all happy.
Oh, okay.
Okay?
Is the B happy?
B is happy with 6. So let's draw water. Needed, available, shared. How many are needed? 8 and 4, 12. How many are available? 8. We're sharing. Divided by 2 tells me there are 2 bonds. All right? Oxygen, hydrogen, hydrogen. Hydrogen's happy. I've used 4 of my electrons. The other 4 electrons go on oxygen. So what is the shape? You want to say it's linear, but it is bent. And the shape, or the polarity. Polar. That is something water. You just have to memorize about water. It's bent and it's polar. Especially when you go AP Bio, it'll help you out.
It's polar because it has
The lone pairs. All right. This one I'm going to change. Let's call this one CH2Cl2. CH2Cl2. Needed, available, shared. So we have 16, 3 and 8 is 24, 18. Right.
How are you doing that?
Everybody's happy with 8. So this one wants 8, and this one wants 8, plus the times 2. So times 2. So 16 and 8 is 24. And hydrogen it wants 2, and there's 2 of them. 28. How many are available? Just go to the valence electrons and see how many are there. So we have 14, 20. So left over is 8. We divide it by. So how many bonds do we have? 4. Who goes in the middle? Carbon. So then I put everybody around it. I put in my bonds, 2, 4, 6, 8. Finish out the octets around chlorine. So 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Hydrogen's happy with his 2. Carbon's happy with his 8. So shape. There's 4 on there. Tetrahedral. And polarity. Huh? I hear both. All right, wait. If I draw a line right there, it's symmetrical, right? But if I draw my line this way, is it symmetrical? No. So it is polar.
How do you know how to set up a
It doesn't matter. Anyway.
So what if you set it up like with the chlorine across each other and the hydrogen?
Yeah, that's what I did.
Because then it would be
It's still symmetrical.
What's weird is the way you're looking at it. You're looking at it as a two-dimensional thing. But if we were to look at it as a 4-dimensional or a 3-dimensional, if we were to take it off of the paper and do 3-dimensional, it's going to look different. Okay? And I'll have the ball and sticks out tomorrow to look at so you can see that. Okay? Yes?
Where does the available come from?
Valence electrons. Let's draw one more. I like SO3. Let's do SO3 here. SO3. So needed, available, shared. Needed, we have 8 times 4 is available. 6 times 4 is 24. Shared is divided by 2 is how many bonds? So sulfur, oxygen, oxygen, oxygen. Put in your bonds. 1, 2, 3. I have an extra bond, so I'm going to put it wherever. So sulfur has his 8. So now I need to make sure oxygen fills out his 8. So that is 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Now the shape is what? No lone pairs. There's 3 of them. Trigonal planar. And the polarity. So what we need to look at this is that double bond is always moving. All right? It's moving here, 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 and these electrons are all shifting. So I would call this a nonpolar molecule because that double bond is just shifting around. There's no one set area of polarity. It's not always in that one area. If it's always being pulled to the same side every time, then it's going to be a polar molecule.
Are most molecules with a double bond nonpolar?
It depends on what's on the other side of it. Yes. Yes. I'm going to do 2 more examples. So this time I want to do SO3 with a -2 charge. SO3 with a -2 charge. So what's the difference between this And this one. The -2, which means I've added 2 electrons to the needed. So now I need 34, but available is now 26.
How did you get the needed?
It's-
You added to it? No, like originally, like when you had 32.
Everybody wants how many to be happy. You need to count how many does it need to be happy.
Okay. That doesn't really help.
Add 2 to both.
Mm-hmm.
So it's the same thing.
Huh? No, it's not. Yeah. Do you have a question? Okay. So shared is going to be still 8 divided by 2, still 4 bonds. So I go ahead and I draw it the same way. So I have 2, 4, 6, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. I have 2 more electrons. If I put them right here, what happens? Oxygen's unhappy. So where do I put them? Always on the central atom. Now you're going to look there, and how many electrons does sulfur have now? 10. Remember he talked about expanded octets? There are just some atoms that will go from 8, they will take into 12 electrons. That is more AP Chem than what we'll talk about here. So this time, what is its shape? It's no longer planar, it's a pyramid. It's pyramidal. And now it's polar. So 2 electrons made it change its shape and its polarity. All right, so get your homework out. We are looking at, I think it's number 5 or the 5th one down. It's CO3 minus 2. CO3 minus 2.
Can I cross out this column?
No, because we're going to go over that tomorrow. So needed, available, shared. So this one we need 3 times 4 times 8 is 32. 34 are needed. How many are available? We have 6 times 3 is 18.
Oh, on the other side.
18, 19, 20, 21, 22, 23, 24. We have 24 available. How many is shared? 10 divided by 2 is how many? 5. This is going to be one of those weird ones. So let's draw it. Carbon, oxygen, oxygen, oxygen. I need 5 bonds. 1, 2, 3. Carbon can get 2 more electrons, right? So right now it has 6. So I can double bond it right there. But can carbon take in any more electrons? No. But it says I need to have 5 bonds. Yeah, this is one of those exceptions where we're not going to have 5 bonds. But let's see if this works out. So we have 24 electrons we need to use. We have 8. We have 9, 10, 11, 12. Oxygen's happy. 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So it doesn't, this is one of those exceptions where that doesn't work. So what is the shape? Shape. 3, no. Planar. And what is its polarity? So it says on the next it has the polarity is what? No lone pairs, nonpolar. Strongest IMF we're going to talk about tomorrow. And then the molecular geometry we said was trigonal planar. Any questions over that? All right, you have your homework.